We discussed up to the reactions of ammonia derivatives. Now, the next one is a special type of reaction known as Beckmann's rearrangement. Okay, what it does, what is the reaction here? Please check. The reaction is more prominent for ketoxymes. Ketoxymes means we have ketone where we have an oxime group present like this. Ketoxymes, for example, if you have phenyl and methyl, let's say, and if we have this group here, these two will become geometrical isomers. So it will be like, it depends upon which group you're writing first. Suppose if you're writing methyl first, then phenyl next, then this can be written as anti methyl phenyl ketoxime. While here this will become syn methyl phenyl ketoxime. So it depends upon which one will you write first. Okay. So it meant that this methyl and OH are opposite to each other. Similarly, this methyl and H are on the adjacent side. So then that is going to be syn form of it. Okay. So what is the overall reaction here is if you take any ketone, any ketoxime, and if I react this with concentrated H plus, then what we expect here is first a protonation will take place from OH2. And now this is the interesting fact here. The sigma star orbital of this nitrogen oxygen bond, that would be much more closer to this R dash bond. So to remove this molecule, that is to remove this H2O, this R minus will facilitate. So on doing so, after doing that, we will get R with C positive charge double bond N with R dash plus H2O. So you can see an alkyl migration has happened. Now this migration is subject to migration is subject to anti-position only. As long as the alkyl group is present on the anti-position, this migration is possible. Okay, and then once we get this part, and that when you do hydrolysis, that is adding H2O, water would attack on carbon position here, getting this as OH2, right? Sorry, C double bond N and R dash. Lone pair of nitrogen will be able to take this H plus and convert that into R, C, OH and double bond NH plus and R dash. And that helps in pushing the lone pair to convert into an amide bond. Thus, it will eventually convert into an amide form. So RC double bond O NHR dash. Got it? So in Beckmann's rearrangement, what has been observed is it has to be on the anti-position only. Then only the reaction will take place. I mean, the migration will take place. Got it? So this is something we need to understand, like, in which case, what type of reaction that is happening. Clear, everybody? Please check the reaction once. Okay. Now, this is Beckmann's rearrangement. Now, if you change just the group positioning, you will have different products. For example, if you have pH CH3 double bond NOH with H plus, in that case, you will report the product as pH C double bond O NHCH3. This is the product you will report. While if you have pH CH3 double bond NOH in H plus and heat, then we will report the product as CH3 C double bond O NH and phenyl. So in the earlier case, this will be methyl N methyl, and here it will be N phenyl. Okay, so accordingly it works. Please check. Next, what are the reagents that can be used here? See, is it always going to be H plus? Not necessary. Reagents for rearrangement. That means what type of medium we can use. That includes only H plus. We can use simply H plus or PCl5 or PF3 or SOCl2. Got it? BF3, B2O5. Okay. Any of this medium followed by H2O. So if you have that, that should be sufficient enough to convert into products. Got it? It is called any protonic Lewis acid. So any protonic Lewis acid will give you this reaction. So please check. Okay. Let me give a few questions here. So please check how we can solve this. Sample. Suppose if you have like this and double bond, I gave you N and OH here, and I gave you H plus and H2O. Then what is the product you will report? You'll only check out what is anti to this OH2. OH2, I mean for O, this propyl is anti. So you will make ethyl, and after ethyl we have a double bond O, and then we have NH, and to that we have 3 carbon group. So this is a product you will report. Okay. Similarly, if you have, let's say, benzene reacting with Br2 and H nu. Okay. So first you will get bromine here, and that on reaction with NaOH aqueous, that will give you OH here via SN2 or SN1, and then using PCC we will get this as double bond O, because it get oxidized, and then using ammonium hydroxide we shall prepare the oxime. And once you get an oxime, if you use H plus and H2O, just now we learned that it will undergo Beckmann's rearrangement, and you'll get N 7-membered ring, and this is the amide formation. Okay, see the structure here from uh, C double bond O onwards. It is alpha, beta, gamma, delta, epsilon. So NH2 is connected from epsilon carbon onwards. That's what is called as epsilon lactam. Lactam is the common name given for um, lactam is a common name given for amides, cyclic amides. Got it? Epsilon lactam, here it is also called as caprolactam. So what you get is a caprolactam form. This is a very standard reaction. So please check what we have to do there. Okay. Next, if there is a chirality present, sorry, notice in case of in case of chiral carbon, in case of chiral carbon migration, configuration is retained. Configuration is retained. Well, what does that mean? Suppose if you have double bond N OH here, and this particular carbon is chiral like this. This is a chiral carbon. Let's say this is plus. Okay, and that you are adding with H plus and H2O. So after migration, we'll get this as CH3, C double bond O, NH with this carbon, chiral carbon, that will still remaining plus. So that means if it was not plus, basically R or S configuration. So if this is R configuration, it will remain as R configuration. Done? Please check. Next are abnormal Beckmann cases. So what are these abnormal Beckmann cases? Okay. Suppose if you have some adjacent carbon being 2 degree, 3 degree quaternary benzyl like that. Okay. So in that case, right? So in case if there is a stable carbocation, let me write down. Okay. In case of 2 degree, 3 degree quaternary, okay, benzylic oximes, then stable carbocation separates out. Stable carbocation separates out. Got it? Okay. For example, if you have R, C, triple bond, sorry, after the migration, we got this as C, triple bond, N, R dash. You got positive charge. This is the intermediate we are expecting. After this, we are expecting hydrolysis should happen. H2O should happen, correct? But what usually happens here is you will get this as cyanide and this part will become alcohol. Okay. Why? Considering this R dash is stable carbocation. If R dash is stable carbocation, Okay. So in case of R dash being stable carbocation, this is what will happen. Let me show you with example. Suppose I have pH twice carbon, and this side we have methyl here, correct? And then I have double bond N and OH this way. And I'm expecting this migration should happen. I have H plus and H2O here. So what do we expect here now? So we expect that first protonation would happen, migration should take place. So we will get this as OH2 plus, and this bond should push, water should come out. And as the migration happens, we'll see that CH3, C positive, double bond N with C. This is CH, CH, pH twice, CH, pH twice. Now, this is what will happen, correct? The minute you try to hydrolyze it, water would attack here, correct? Making this into CH3. Sorry, the minute we try to hydrolyze here, so what will it do? This bond will immediately close into triple bond and water will attack here on the carbon. So we will get this as CH3, C triple bond N plus pH, CH2, pH twice, CH and OH. This is a connection you will get. Of course, you can make it as a separate carbocation and then write down the water content. Clear? So this is what will happen. Okay. So instead of showing it here this way, so we can expect that the bond will break here, form cyanide will form, and this group will separate out carbocation. I hope this part is clear. So one interesting question on a similar idea that has been asked is this one. Please check how this question has been asked. So in a bicyclo form, correct? In case if you have a double bond here, N and OH is present on this end, okay? And here you have methyl, and this is how the bicycle group is given, and it's been given with BF3 followed by hydrolysis this way, okay? So first the kind of protonation BF3 will get attached to it, okay? So let me just copy this part. Sorry. So here we have O, BF4 minus N plus here, okay? Then this bond will break and convert this into triple bond here. This bond will leave. So that will make this molecule into. Now check this out carefully. This is 1, 2, 3, 4, 5. A 5-membered ring will still remain. And this said on the 5-membered ring on these two positions, correct? One position it has been lost and the other position we still have the molecule. So let me write on that. So this is that 5-membered ring. It has two groups here this way, okay? And one side I have a methyl group with a carbocation form, and on the other side, correct? On the other side here, it has methyl and carbon with C double bond N with positive charge here. Got it? One second. Right. So we will get here as triple bond on this position. Sorry. So we have this carbon connected to one more carbon and one more carbon, carbon and one more carbon, and that is converted into a cyanide form. And then the hydrolysis will make this molecule to get OH on the other side. Here you will get this as OH, correct, after hydrolysis. So this is a product we will report. Okay. Now, next, this is an abnormal case. Another abnormality is in case of aldoximes. Suppose if you have an aldoxime, okay, uh, H plus will be released and cyanides are formed. So here amides are not formed, but cyanides are formed. How is that? See, if you have R, H, double bond N with OH, or even if you have R, H, double bond N, OH, which means it doesn't matter whether it is anti to H plus or not, whether it is anti to hydrogen or it is syn to hydrogen. Both the cases, first the protonation will take place. It will become OH2 plus, OH2 plus, and now see the migration. This bond will break into formation of cyanide, water is removed. Here also cyanide, water is removed. So in both cases, the product is the same. That is R, C, triple bond, N plus H3O plus. Correct? So in any aldoxime, it does not depend on which direction it is, whether it is anti-bonding or not, you'll always get the same product, right? I'll give you one more case here. Last example, check. In case if you have group like this, benzene, right? And I have 5-member ring this way. Here I have double bond N and OH with 2 methyl groups on this end. That on protonation, I mean we have H plus and H2O. Check what is the product you can get. And same case, I'm putting the same case here, but only thing that I'm changing is the OH positioning this side. This is the positioning what you get. In the first case, the migration is appeared quite nicely. That means OH2 plus will form here, right? So I'll write it this way. OH2 plus will form here, and this group will get migrated onto this position. You will get the product as a 6-member ring now, directly connected to nitrogen. So this is a 6-member ring which is formed. So it will be NH, double bond O, 2 methyl groups here, benzene here. So this is a product that you will report it out. Correct? That while if you have it on this end you know that what will happen. If you have it on this side, so because that there is a stable carbocation form OH2 plus, this bond will migrate to make it into cyanides, and other side we will get this way. You will get carbon with cyanide here, and this side we have one carbon, two carbon, we have 2 methyl groups on it, and OH. This is the product form. Okay, please check. Done. Okay. Last thing, please check the note here now. We learned something about erythropine already. Got it? Erythropine is basically a fused ring in chair conformation, isn't it? So, erythropine, which we formulated as CH2 6 times and N4. This one, hexamethyl tetraamine form. Okay. This is used as urinary urinary antiseptic. Urinary antiseptic. And second one, if you compare benzaldehyde to react with ammonia. Okay, consider we have sufficient or excess amount here. Just a minute. Check. If you have something like a benzaldehyde here, react with ammonia. So what do we get? As you react with ammonia here, so we will get, see, we expect this to form something like PHCH double bond NH, correct? But this will not be stable because imines are generally unstable. So it would keep on reacting till it becomes the most stable form. And the most stable form is like this: PH, then we have CH double bond N, and that is connected to one more carbon with here having CH double bond N, another PH, and one more we have, mm, sorry, this side we have PH. Directly, this is connected to PH, and the other side also we have N double bond CH PH this way, correct? So this compound is what we call it as hydrobenzamide. Hydrobenzamide. All right. Last thing of a similar reaction, if you notice here, just like hydrobenzamide, in case if you have 3 moles of aldehyde, let's say if I take 3 moles of formaldehyde, acetaldehyde, and then you react with 3 moles of ammonia, okay, with an appropriate pH, then first it will become 3 moles of CH3, CHOH, and NH2 to start with. Then then the dehydration should happen, right? So which will convert into 3 moles of CH3, CH double bond NH, which is the imine form. And this 3 moles of imine form will convert into the cyclic structure like this. We have N and N here, and that group connects with the other N here. Just like erythropine, we have those 3 nitrogens. It is the same thing which you will get. This one. Okay, this is the product form. This is the trimerized product. Amine form. Okay, these are very special reactions, so just remember them directly. So 3 reactions. One is with formaldehyde, benzaldehyde, and acetaldehyde. Formaldehyde will give you most stable form as erythropine. Benzaldehyde will give you hydrobenzamide, and acetaldehyde will give you trimerized amine. Okay. So guys, this is about Beckmann's rearrangement. Now, let's look into reduction reactions. In fact, we have come across reduction reactions before. In alcohols, we have done the reduction reactions in alkanes everywhere. Just check out the reagents that we are using. Okay. Mainly, you need to emphasize on the reagents here. Got it. So when it comes to Clemmensen's reduction, you know that we will use zinc mercury amalgam, and Wolff-Kishner we use hydrazine in KOH glycol. HI red phosphorus that also reduces everything to alkane, and then we have Mozingo's reduction where that reduction will give us uh, alkanes as well. Okay. Mozingos we just recently learned in the same preparation cases, correct? As one of the reaction cases of aldehydes and ketones. Okay. Now let's see what are all the reduction reactions in generally, correct? Other than that, we learned the aldehydes and keto forms. If at all you want to convert into alcohols, everything we learned in alcohols chapter, right from lithium aluminum hydride, NaBH4, MPV reduction, pinochle formation, sodium in ethanol, which we call it as Bowell-Blanc reduction. Correct. All of these reduction reactions we have learned it already. Next. Now let's notice what are all the oxidation reactions in general. Correct. So when it comes to oxidation reactions, which all cases are observed as oxidation? Let's see that. Right. See, starting with KMnO4 and H plus. So if you have KMnO4 H plus or KMnO4 OH minus and KMnO4 H2O, what is the reactions that happen? So first, if you have any aldehyde under oxidation with any of these reagents, it will convert into carboxylic acid. If the aldehyde is glyoxal like this, first the oxidation will convert into oxalic acid. Oxalic acid will further get oxidized to 2 moles of carbon dioxide. Alright. This is about aldehyde forms. In case if you have ketone, if only KMnO4 H plus is given, no heat is given, then no reaction. But in case if H with KMnO4 and heat is also given, KMnO4, it doesn't matter whether it is acidic medium or basic medium, if heat is given, no H here for this ketone, then you will see different products. The product is CH3COOH of 2 moles. How is this forming now? See, what you need to understand is that for ketones, correct? Suppose if this is an ketone example, ketone, imagine that on subject to heating, either in H plus or OH minus, it will start showing sufficient equilibrium form of enol, right? It will start showing an enol form. So enol will be this side or enol will be on this side like this. These two are the enol forms which you will notice. Correct. Now, the minute you get a double bond form, KMnO4 will be able to break this bond here. So we will get this as if KMnO4 break the bond here, right? Break the bond here. So what do I get? In the first case, I will get this as CH3, CH3COOH of 2 moles. And in the second case, we will get this as CH3, CH2, COOH plus single carbon will convert into carbon dioxide. Okay. Now, there is a very important point that we need to note here, which is called as Popoff's rule. Popoff's rule. So, Popoff's rule suggests that, okay, major product will be formed in the direction of formed in the direction of smaller carboxylic acids. smaller carboxylic acids. Now notice, in when you break the first case, you got 2 moles of acetic acid, which is 2 carbon acid, while in the second case when you break, we are getting a 3 carbon acid, right? So which means, which is major here? This one is major and the other one is minor. That is Popov's rule. The Popov's rule is another, I mean, it is another way, a disguised way of explaining that you always go for the more stable enol. So same thing is, go for more stable enol, more stable enol, and then break the bond. Okay, then you have to break the bond here. Okay, so let me show you more questions that way. Suppose if you have a double bond, sorry, a ketone here with a double bond like this, correct? So you know that the more stable side is on this side. So when I react this with KMnO4, KMnO4, H plus, and heat. So what do we do? First you write it into the enol form and then break it. So after breaking is, so you will get this into left hand side, you will get into a ketone form. Ketone. This side you will get into a ketone form, and here you can see 1, 2, 3, 4, 5. So we have this as 1, 2, 3, 4, 5. Fifth position will be acid. Now this will get further oxidized. Again a keto form here. So H plus and heat, which if you have with oxidation. In that case, if I put the enol form one more time on this carbon, so the enol will be more stable on this side. And again you break the bond here. So as you break the bond here, now you'll have 1, 2, 3, 4, 5. 5 carbon. So COOH, here COOH, and the other one which you will get is CH3COOH. So this is a product what you will get, guys. Okay, so you keep on doing it till you keep on doing it till you get the smaller carboxylic acids as possible. So I hope the KMnO4 cases are clear, everybody. Please look into it. All right, these are all the strong oxidations. Other strong oxidations, see, other strong oxidations which does the same reaction, same reactions include K2Cr2O7 H plus and heat, strong heating. Okay, concentrated HNO3 and strong heating. Clear? CrO3 H plus and strong heating, or H2CrO4, H2CrO4 and strong heating. See, either it is given in this format, this format, this format, or this format. In all this format, you'll get the same product. Done. Please check that. If you have a doubt, you can ask me now. Everybody, please check once properly. See, the next reaction is oxidation by selenium dioxide. Selenium dioxide in acidic medium is another very important oxidation part. Suppose if you have CH3CHO and we use selenium dioxide, okay, with CH3COOH, correct? So that will form glyoxal, or C double bond O, C double bond OH. This is glyoxal. Basically, what it is doing is, okay, oxidizing alpha uh, alpha carbonyl alpha carbon to aldehydes or ketones. Okay, how is this happening? Please check. So if you notice the mechanism, SCO2, when you treat that, I mean, when you keep it in water, it will be selenous acid. So that is S double bond E, OH and OH. Just like sulfurous acid, this is called as selenous acid. Selenous acid. Okay, correct. So if you have CH3, C double bond O, CH2, CH3. Okay. Now, suppose if you have this compound, for example, in that case, you write the most stable enol form. You are keeping it in acidic medium. We can expect this to have this enol form like this. Right? Now, once you have this enol form, check out this enol form. Okay. So this enol form, as it reacts with selenous acid, how does it make a reaction? Check. So we have uh, OH here, OH, Se, and OH here, and double bond O here. So first, this OH2 will be lost as H2O, right? And as soon as that is being done, so pi bond from here will attack on this oxygen, pushing the electrons on selenium. Okay, why? Because this will come out as water molecule. In that case, what is the product that you are getting? You are getting this as CH3, C double bond O, then CH, CH3, and now here we have connection of oxygen with selenium and one OH group. H2O has been lost. H2O has been lost out of it. Okay, minus H2O. Correct. And once you have that here, so you can see the hydrogen present here, the hydrogen which is present here. So oxygen will try to push back electrons towards carbon. Correct. Oxygen will try to push back electrons towards carbon. And OH group, because OH group will, sorry, reverse. This OH group on selenium will try to take this H plus, pushing the hydrogen bond into double bond formation, and selenium will take away electrons here, correct? And water will come out of it. So that makes it CH3, C double bond O, CH3, CH3. So selenium plus H2O. Okay. So check out properly. Selenium got completely reduced and you got this as alpha keto formation. Correct. In case of unsymmetrical form, if you have, okay, another example. Suppose I have an unsymmetrical, if you have any cyclic structure, we have like this. In that case, selenium dioxide will give us double bond O and double bond O. Okay. And in case if you have unsymmetrical form like this, we have double bond O. Always go for the more stable enol form. More stable side will be this side. So this is major. The other side will also be forming, but this is major. Done. So very simple case. Selenium dioxide is not that difficult. If you just need, if you just know where the group has to be attached, so that is very easy. Clear, guys? Next, the third reagent for oxidation is bare vinegar oxidation. Bare vinegar oxidation is specifically for ketones, where in case if you have any ketone like PHC double bond or CH3, let's say, if this ketone is subject to peroxy acids, something like CF3, C double bond O, OOH, let's say, and this is an isotopic oxygen. In that case, we will get PHO, C double bond O, CH3. Okay, star would be here, and this will become CF3COOH, correct? Which means there is an insertion of oxygen, insertion, insertion of nascent oxygens between alkyl groups, right? So that is what will happen. So check out the mechanism. How is this happening now? So if you have pH C double bond O CH3, this is how it is. And now we have HO O C double bond O, let's say CF3 here. This is the way it is, right? This is a localized oxygen, right? This is a star oxygen, but it is localized electrons. Since it is localized electrons, chances are it will attack on carbon and pi bond will shift here. On doing so, we will get pH C CH3 and O minus, and here we got connected with OH with O C double bond O CF3. Okay, here it is plus. So obviously this minus will take away H plus from here. We will get this as pH C CH3 and O minus. Clear? Sorry, OH. No, no, sorry. It is not taking H plus from here. Sorry. O minus here. Okay. Once you get this O minus here, uh, here it is fine. This will take. Here it is OH in the bottom carbon. Here O and C double bond O CF3 will be present. Now check this case here. You know that peroxy linkage is very weak, and we just got this is the star oxygen, and this is a peroxy linkage. It's a very weak linkage. So naturally, this oxygen will try to break the bond here. Okay, as it breaks down, right, this oxygen is starting to suffer getting a positive charge. So somebody should help it out. That is where you will see the phenyl will start migrating here. And in that case, the carbon will suffer. That is when the lone pair of oxygen will push the electron here. And this is exactly what happens. So we will get this as PHO and PHO connected with C double bond OH plus and CH3, and the bond which has broken will be O minus C double bond O CF3. That's how it broke. And this C minus will take H plus from here. That results in making it as PHOC double bond O CH3. So an ester is formed. So Baeyer-Villiger oxidation is about generating esters from ketones. So if you want to generate esters from ketones, this is the reaction that you will do. So CF3COOH. Please check the reaction quickly. The mechanism is clear. Right. So check this out. This is about Bayer vinegar oxidation. Now notice, now notice this. Here, why only phenyl got migrated? Why not methyl? Because both of them are at the equal, same distance. Same thing would happen. So here we need to learn what which one will migrate over the other. So known as migratory aptitude. Migratory aptitude of Bayer vinegar oxidation. So if you compare the migratory aptitude, the H minus definitely has the highest ability to migrate, correct? So H minus has the highest ability. Then it is 3-degree alkyl, got it? Then it is 2-degree alkyl, okay? Then it is anything like phenyl groups. Within phenyl group, phenyl with electron donating group and only phenyl, and phenyl with electron withdrawing group, correct? This one. And then we have 1-degree alkyl group, correct? Then we have CH3 minus, and last we have R C double bond O. This is the migrating aptitude. Clear? So let me push you some examples how we can do this. Check. First one, suppose if you have pH C double bond O, C double bond O, CH3. If this is how the group is. And then you treat this with some acid R CO2 OH. And here is the isotopic oxygen. In that case, migration would best happen between these two positions. That is major. This is an exceptional case. That is pH C double bond O O C double bond O CH3, and this is identified as major, and this is an exceptional case. Okay. Otherwise, anything that is there, it will always follow the same. Suppose if you have ketones, and I have, let's say, pH CO3H. Okay. And within that CO3H, let's say one is isotopic oxygen. In that case, you will get this into a 6-membered ring like this way. So you will get into an ester form. Suppose if you have same thing, but I have methyl on one side this way. So in that case, it will come between that methyl case here. This is the major product. Fourth one, if you have simply ketone here, and then we are reacting with pH CO2OH. In that case, we will get this as O here and ethyl here. So this is the product formation. Okay. In case if you have some alkyl here, suppose a benzene here, like this methyl, and then double bond O and H here, and then you are treating with pH CO2OH with a star. This is also star. So in that case, we'll get pH C double bond O OH. In this case, hydrogen migration is most easily observed, and you'll get this into an acid form. Okay. Clear, everybody? Please check. These are all the cases of Bayer vinegar oxidation. Please check quickly. Finished? One second. Let's see the next reaction. See, I have given you the list of all the reducing agents. Okay. This you should have a copy. I mean, if you have a printout already, this will really help you understand in which case, suppose if this is a reagent, if you react with what reactant, what is the product forming. That way, I have listed out all the reducing agents here, correct? Whatever that is there in a syllabus, including dival H up to this 16, please go through it once. Now, come to the next part, which is about tautomerism. Tautomerism is something which we have learned it earlier. Tautomerism, especially here, we are focusing on keto-enol form only. Keto-enol form. So, ketones from simple aldehydes and ketones, they will form enol. That is, this is keto form, this is enol form. And the amount of energy difference between them is not very high. It is just 50 kilojoules per mole of difference in differential energy, which suggests that delta G, which is, if K equilibrium is 1 by 99 or K equilibrium is 99, that means either completely ketone is present or completely enol is present. Okay. So if you write K equilibrium as 100, 99 by 1, which means we are expecting all of the enol is present, ketone is hardly present that way. So if I have to convert percentage wise, then I can say the amount of energy required to interconvert almost from 1 percentage to 99 percentage does not require a lot of energy. Okay. So this energy can be compensated simply by intra-hydrogen bonding or resonance or aromaticity in enol, which means if you have any enols which are getting stabilized by maybe hydrogen bonding or maybe resonance factors or aromaticity, it will drastically increase the enol content. You will not easily find a case where you will have only like 30% ketone, 70% enol, or vice versa, correct? You will not find 50-50% cases also, very less. Most of the time you will find a large quantity difference. So 80%, 20%, 90%, 10%, any of one side, because it's very easy to push in any one of the directions depending upon stability factors. So first check out active methylene group. For example, if you take this ketone and you notice the enol percentage here. So in this case, the percentage enol due to hydrogen bonding and extended conjugation. See, there is an extended conjugation here, lone pair pushing here, pi bond pushing here, this pi bond pushing here. Because of this, this particular active methylene ketone will showcase almost 76% of enol. Now, if both side hydrogens are there, the reactivity is even stronger. That makes it almost 98% of enol. If one hydrogen, one methyl is there, it is around 84%. Both methyls are there, that means you are talking about ketone. Here only aldehydes, aldehyde ketones, here it is only ketones. The percentage decreases to almost 76. The minute you come across ester, right, ester will have a least enol content, because if you try to make an enol here and make a hydrogen bonding, the extended conjugation is weaker here as the OET is already supporting it. So that makes it weaker. So it will be like only 8.3%. Okay. And next, if both sides, if you have ester, the enol content is hardly observed. And if you have both sides phenyl, right, the content is almost 100%. So these are the first type of cases which are active methylene cases. Keep that in mind. So in all active methylene cases, how the percentage enol is changing. The very standard question which is asked as a complete trend of the percentage enol. Hmm. Next, aromaticity. See, in the first case, if you write the enol form of it, I'll write down the enol form here. So what do I get? The enol form would be like this. So there is not much of conjugation help. In this case, if at all I have to write the enol form, it will be double bond. Sorry, it will be like OH here and double bond here. That means hydrogen from here, I migrated hydrogen from here. Okay. So if I push the minus charge here, that minus will become double bond here. This will move here. This will move here. Right? Sorry. This is the way I have to write. Yeah. This is the enol form. In the case 3 here, the enol is completely in this particular form, which is aromatic. Therefore, now if you compare the percentage enol here, so we see the percentage enol in this case. C has the highest percentage, then B, then A. Okay. In fact, this enol percentage is almost 100% because of aromaticity. Aromaticity will always give you huge amount of stability. Okay. So this one is almost 0%. This one is almost 100%. Next, if you have bridgehead positions. In the case of bridgehead positions, you can see this is the position where you can have an enol. Unfortunately, although there is a hydrogen present, as per Brett's rule, you cannot get a double bond on any of these directions. So there is no enol content here. Here there is some enol content. Here there is some enol content. Here there is little bit more enol content. Okay. So we can say that percentage enol content, okay, in C would be slightly more than A, then sorry, C, then B, then A. Okay. Next, ring chain effect, correct? So whenever you have a ring form here, the percentage enol that has been noticed in this case, this was found to be 0.02 percentage. This is found to be 10 raised to power of minus 6 percentage, which clearly suggests that a ring form will always have a better stable enol. So therefore, percentage enol wise, this one is the more form. Okay. If this is confusing you, one second, I'll write the enol at the bottom here. Correct. So what is the enol form here? The enol form will be like this. This enol is greater than this enol. Next, steric relief. Suppose if there is a mesityl group present on carbon, and imagine there are two mesityl's present here. This entire mesityl group, I'm calling it as MES. So one MES here, one MES here. So between two mesityl groups, there will be huge, strain because expected angle is 109 degrees. But because of such bulkiness, these group and these group will always have van der Waal repulsions. If by chance this 109 degrees is converting into 120 degrees, that will release the strain and suddenly increases the enol percentage. That's why steric relief cases, this one is also 95% in. Next, if you have a 5-membered ring with diketone here, second, sorry, check out. This is keto form and this one is the enol form here. Now, if you notice, in this enol form, there is a strong hydrogen bonding as well as, there is a release in the strain. What kind of strain here? Check out. This lone pair present here and lone pair present here will have strong repulsion due to the eclipsed form. They exist in an eclipsed form. Now, suddenly, that eclipsed repulsion is gone as well as a hydrogen bonding is developed. That's the reason why this part of the enol will be almost 100%. While if you take the similar case but in an open chain, okay, in an open chain case, Problem here is to avoid this repulsion between these two, it will always stay in anti form. This is the anti conformation. Okay, got it. So it will remain always in the anti form. It never gets to the eclipsed form. Right. So if it does not come into the eclipsed form, we cannot have hydrogen bond. That's the reason why it will always hold itself to keto form. So see, both looks exactly similar case, but slight difference here. The minute it gets cyclic, enol is 100%. The minute it is acyclic, then ketone is 100%. Okay. Next, what about solvent effect? See, ketone has more polarity than enol. Generally, C double bond O has more polarity than C double bond C and OH. Hence, polar protic solvents will always increase the keto content, and polar aprotic, non-polar or gaseous medium, they all will increase the enol content. This is best example. If you notice this diketone, in the gaseous phase, the enol percentage is 92. In the non-polar solvent also it is 92. In its pure liquid form, it is 76. The minute you put it in water, it has become 15 percentage. This year, there was a JE question exactly on this same uh, molecule. So for this molecule, he has asked what will be the percentage amount of, not exactly the percentage. They said the comparison keto versus enol in aqueous solution. Even though there is a hydrogen bonding here, the minute you put it in aqueous solution, the enol content decreases. Next, and some enol content of these molecules, if you notice, these will not show any kind of enol content. One more case, I'll write down here. Even if you have a diketone like this, so this does not show any enol content. Okay, because if you get a double bond here, right, or double bond here and here, this will become anti-aromatic, same as this one. So this is anti-aromatic form. This is also an anti-aromatic form, anti-aromatic form. Okay, here there is no hydrogen at all. And esters usually does not show enol form. Okay, so these are all 0% enol content cases. Okay, this is just a quick brush up. All everything of this part has been already learned before. So now tautomerism always gets enhanced or catalyzed when you use acidic medium or basic medium. For example, when it comes to acidic medium, what will happen? In case of acidic medium, if you have ketone, okay, with H plus, the lone pair will take H plus first here. It will get protonated on oxygen here. H plus will be present here. And now, if you notice that CH2 and H, this is the molecule present, okay, and water in aqueous solution, I mean, this is acidic solution here, which has water content in it. So that will take the H plus here, pushing the bonds onto this side, thus converting into an enol form like this. So notice there is an enol which is forming here. And the reverse is also same. Reverse is also true. That if you start with enol, let's say you start with enol here, and then we have water molecule. I mean, then you have H plus here. So in that case, the lone pair on this oxygen will push here. The pi bond will take away H plus. That will convert into double bond OH plus, and this will become CH3. And this will lose away H plus in the solution and convert into ketone. So you can see ketone to enol conversion, enol to keto conversion. So it will exhibit in equilibrium. So there is an interconversion of these two. Now notice base catalyzed mechanism. When it comes to base catalyzed mechanism, we have double bond O, CH2 and H present. Basic medium OH minus will take away H plus from here, and that will form double bond O, CH2 minus. Okay. That CH2 minus will be pushing here to get this as O minus. And this is not basically some new intermediate, it is just a resonating structure. So you will get this as O minus and double bond. Now these two resonating structures, these are called as enolate ions. Enolate ions. Okay, or enolate ion, just the ion because it is just a resonating structure. Now this enolate ion in aqueous solution, correct? So that will take the H plus from here and thus convert this into an enol form. So directly enol will not come. So first an enolate ion is formed and then enol will form here. If you notice the reverse mechanism, that is if you already have an enol like this, and if you use basic medium, this OH minus will take H plus and we will get O minus double bond here. That will push the electron here, pi will come on this side, and that's how you will get double bond O and CH2 minus. And this CH2 minus will take H plus from the water here, and that will convert into keto form. So you can see this is again enol to keto. So you start with ketone, end up at enol, or start with enol, end up at ketone. So note one important aspect here. In acid catalyzed mechanism or base catalyzed mechanism, which is much better, acidic, acid catalyzed or base catalyzed? Please check out that part here. In the case of this, there is a certain carbocation character here because the pi bond can shift on oxygen. This gets positive charge. So formation of this enol is less likely to happen. That means the rate will be slower. While in the base catalyzed, there is no such carbocation formation. It is forming an enol successfully. So that means we can say rate of base catalyzed mechanism, rate of base catalyzed tautomerism is better than acid catalyzed mechanism. Then, right. So this is the part you need to understand. Please check quickly.